Hello everyone and welcome to another installment of your favorite online computer science live stream. How you doing, Laura?
I'm doing very well, thank you, Pete. How are you today?
Very well, thank you. Excited for the show we have in store today?
Me too, Pete. We are at the point in our live streams where we are now bringing back recurring characters. We should call this episode the reunion special.
Yeah, on that note, I've been thinking we should add a bit more showmanship to our guest introductions.
Okay, what have you got in mind?
Well, I thought we could trial a boxing introduction.
Ooh, not sure about that. You mean something like this? Introducing our special guest for this afternoon. He is a former host of the show with over 100 videos created for the site, countless topics written and questions created. He lives and breathes in code. He is the human MacBook, the Canadian computer cowboy. Please give it up for Mac, the Enigmac Bowley.
Hey everyone, it's great to be back. What an introduction. I don't know how I'm going to live up to that for the rest of this.
What would you be taking us through today, Mac?
Today we're going to be looking at bubble sort. We're going to do kind of 2 live streams over the next couple of weeks looking at some sorting algorithms, and today we'll be learning about one of the kind of main standard sorting algorithms covered in GCSE Computer Science, bubble sort. We're going to learn about terminology for algorithms, how to trace them, and discover how efficient they are for completing a task.
Fantastic. If you have any questions for Mac as he's presenting, remember you can send them in the chat or you can use the question form below. And Mac, when you're ready, you can take it away.
Absolutely. Cool. So we're going to, look at bubble sort today. So I always like to start my presentations with some questions. I think it makes it easy for you guys to know what you're going to learn, and it also kind of piques your curiosity a little bit. So some questions we're going to answer over the next sort of 15 minutes or so. The first one is why we need to sort data in the first place. We're going to look at sorting algorithms, but why do we even need to sort data? We're going to talk about bubble sort and what it is. We'll then look at why it's called bubble sort. This is quite a common question I get when I'm teaching people about bubble sort. Why is it called that? We're also going to look at how we can trace a bubble sort, trace the algorithm, looking at variables. And finally, we're going to talk about how we can look at the efficiency of algorithms. So what sort of things we're looking for, and then we're going to use that to see how efficient bubble sort is. So let's start off with the big question. Why do we need to sort data? Well, if anybody was here for the last live stream with Di, you'll know that one of the big uses for sorting data is so that we can search it efficiently. If we don't have a sorted data set, we can only use linear search. But if we can sort the data first, it means we can be a lot more methodical. We can be a bit more efficient with how we find things. It's also great for displaying data. So if we need to show any data to a user, showing it to them in a jumble, in a random order is really, really frustrating. And so we can give it to them in a sorted order, and that makes it easier to sort of process, especially if it's a lot of data. And finally, sorting data allows us to do analysis. So putting data in order allows you to do things like find the median value. It allows you to sort data sets by kind of different parts of it, right? You might sort it by name at first, then maybe age. You can sort through different things to get different analysis of the data. But mostly the reason that we sort data is because unsorted data is super frustrating. So it makes us make this sort of face. But luckily, we aren't the first people to come across this problem. Now, computer scientists have been having to deal with sorting data for a really long time. And so luckily, they've come up with some kind of standard ways to do it. There's lots of standard sorting algorithms, some of them that you will learn about during GCSE Computer Science, some of them you won't, but it's good to know that they exist. So we have sort of bubble sort and merge sort, insertion sort, quick sort, which I think makes you want to use it just from the name. And then finally, my favorite, which is Tim sort, which was invented by a guy called Tim. But today, we're going to start exploring sorting algorithms by looking at bubble sort. So it's usually the first one that people see, and we'll see why in a minute. I'll kind of come back to that question. So what is bubble sort? Bubble sort is a brute force sorting algorithm. at its core, in order to sort data, like if I was to give you two sort of items, two numbers to sort, the way you would do it is you would compare them, and then you would see which is larger or smaller, depending on which way you wanted to sort them, and then you would swap them, right? So that's the sort of core, the simplest kind of sort. If we just had two things, we'd compare them, and then we'd put them in the right order. Now, bubble sort works very, very similarly to linear search, right? It goes through a collection one by one, comparing them and then swapping them, right? So it goes from start to finish and it compares them and swaps them. And it keeps doing this until we've ended up with a sorted list. So that's why it's called brute force, right? Because it goes from start to finish and it does it sort of very procedurally, one after another, very similar to linear search. So I'm going to talk you through a little bit about how this works using an example to start with. Before we sort of dive into code, I think it's really useful to see how it works in action to get an idea of what a bubble sort is, and then we'll kind of jump into a little bit of code and pseudocode later. So here is a collection of data that we want to sort. These are cards with numbers on them, and we want to sort these cards into ascending order. So we want the largest cards to be on the right-hand side where the 1 is right now, and the smallest to be on the left-hand side where the 9 is right now, right? So we're going to use bubble sort to achieve that, right? We're going to sort these into ascending order. So like I said, bubble sort sort of goes from the beginning of the collection to the end, comparing two items at a time. So the very first step is to compare the first two items in our collection, right? The 9 and the 3. And what we do is we say, is the 9 larger than the 3, right? And if it is, we're going to swap them. And in this case, it is larger than the 3, right? So we've compared them, see if the 9 is larger, and then we're going to swap them. So you'll see in the next bit, the 9 and the 3 have now swapped. And now we're going to repeat that process, right? So we're going to look at the next two items. So the 9 and the 10. We're going to say, is the 9 larger than the 10? In this case, it's not. So we're not going to swap this time. All right, so you can see the sort of procedure here. It starts from the first two items and it's going to work its way up. So next we'll go compare the 10 and the 2, and we'll say, is the 10 larger than the 2? And it is, so we're going to swap those. Then we'll do the 10 and the 8 and say, is the 10 larger than the 8? It is. The 10 and the 5, 10 is still larger than the 5. And 10 is definitely larger than 1. So you'll see we sort of picked that 10 up, and we've carried it with us through this first part of the algorithm. So when we reach the end of the list, right, we're now right at the end. We've put that 10 on the far right-hand side. And one complete go through a list is called, or through a collection, is called a pass. Now, when we do sorting, well, usually we're going to do multiple passes, particularly with a brute force algorithm like bubble sort. So after the first pass, our 10 is in the correct position. So you'll see it started in this third position here. And by the end of the first pass, it was all the way at the end. So this, I'm going to take a pause here. I'm just going to answer one of our key questions from the beginning, which is, why is it called bubble sort? Now, when this algorithm was come up with, when the people came up with this algorithm, they, need to come up with a name for it. And they thought, right, what does this resemble? This sort of largest item moving to the end of the list. And I thought, it's a bit like bubbles in a fizzy drink, right? So when we have a fizzy drink, you'll watch the largest bubble sort of collect and rise to the top, right? And that's what they thought bubble sort looked like, right? The largest item was sort of bubbling up to the top. So that's why it's called bubble sort, because they thought it was a cool name and it resembled bubbles in a fizzy drink. So there you go. That answers the question why it's called bubble sort. So if we were to do another pass, right, repeating that process and comparing two items at a time, the collection would look a bit like this, right? So now the 9 has moved into the correct position. So it was at the start to begin with, then moved it up one position after the first pass, and now it's been picked up just like the 10 was before and moved to the second last position. Now, I'm just going to get one of my hosts to come back in with me because I have a quick question. Hello, Laura.
Hi, Mac.
Hey, so after 2 passes, we've got 2 items that are in the correct position. So I just wondered, Laura, how many passes do you think it's going to take to sort every item in this collection? So there are 7 cards here. How many passes do you think we need?
I think it's going to take 7 passes, Mac, because there are 7 cards in the list.
Sweet. I think that is very logical. Let's have a look. We're going to go through the rest of these passes and we'll see if Laura is correct. Thank you so much, Laura. It's good to see you. So, So after the third pass, the 8 would be moved into the correct position. After the fourth pass, the 5 would be moved into the correct position. After the fifth pass, the 3 would be in the right position. And then we're on the sixth pass, and we see the 2 is in the right position. Now, you might notice something here. We've only got one card left that is technically unsorted, right? The 1. But because all of the other cards are already sorted, the 1 is actually in the correct position already. So the maximum number of passes needed to complete a bubble sort is equal to the number of items in the collection minus 1, because that last card is already sorted once all the others are in there, right? So in this case, we only needed 6 maximum passes. Cool. So now that we've seen a bubble sort in action, we've looked at how many passes we need. I'm going to jump into a little bit of pseudocode now. Now, before we do that, I wanted to just go over a little bit of key terminology with you guys. Now, I tried to use the word collection before. You might have noticed I slipped a couple of times when I called it a list. But when we are coding a bubble sort or coding any sort of sorting or searching algorithm, we need a collection of data. And when we're doing that in programming, we need to use a structure like an array or a list. So the structure is an array or a list is the structure that we store all the data that we need to sort in. An item is an individual piece of data within that structure, right? So when we need to talk about individual pieces of data, we'll call them items. And then finally, we're going to use indexes. So that's the position of an item in the structure, right? So we all know in arrays and lists, indexes start at 0. So the first item will have the index 0, and then it will count up from there. So just a little bit of terminology that I'm going to be using going forward, and I just want to make sure we're all on the same page. So here is the bubble sort pseudocode. All of this pseudocode is taken directly from the Isaac site, so please go check it out if you want to review it in your own time. All of these are taken word for word from the site, so I haven't made any changes, so you can get at this whenever you need it. So here is the full sort of bubble sort pseudocode as we've just seen it. Now this is a lot to take in at once, so let's break it down a little bit. So to start off with, we need to count how many items are in our collection, right? So the very first thing we do is we check the length of our collection, which is named items in this case. And then we get a count of that and we store it in the variable num items. We then have an outer for loop. Now the outer for loop is going to control the passes, right? It's that going through each pair of items in a list one time is called a pass. Now this outer for loop is going to count up with each pass, right? So that's why we use the variable pass num, right? So as we go through, as we do more and more passes, that pass num is going to go up by 1 each time. Now inside that outer for loop, we have a second for loop, an inner for loop. Now this is what's actually going to perform the pass, right? This is what's going to go up 2 by 2 up the collection, comparing the items. Now you'll notice that the outer for loop goes from 1 to num items minus 1, like we just said with Laura, right? Goes to the number of items minus 1. So on that 7 card collection, it would do 6 passes. The inner for loop goes to num minus 2, right? Now, when we're doing a bubble sort, we're comparing items 2 at a time. So we actually don't need to go all the way to the end of a list. We just need to go to the second to last item because we're doing them 2 at a time. So here's an example of that with our cards, right? This is the last comparison we do, and we're doing the 2 last items. So we say number of items minus 2 for each pass that we're doing, right? So the outer for loop is the passes. The inner for loop is what actually goes through the list comparing the items. Now, we have an if statement inside of that inner for loop that compares our 2 items. So we have the index that's counting up as we go, and we're going to compare the item that's at the current index with the item at index plus 1. Right? So that's how we do 2 things at once. And if the item at our index is larger, we're going to swap them, which is what happens in here. Now, we use a temporary variable for this. When we want to swap the items, we can't just sort of overwrite them. So we need to use a temporary variable to hold on to it for a little while. Now, that's a quick go through of the bubble sort pseudocode. Now, if you're given this, you might need to trace it in an exam or in class when you're learning a bubble sort. So let's have a look at what that looks like. Now, I don't have time in my sort of presentation today to kind of step through a whole trace with you. So I thought I'd show you what one might look like and then encourage you to have a practice of this using the Isaac site or with your teacher in class. So this is a trace table that we might use for a bubble sort. You can see we've got a column for pass num, for our current index, and also for that temporary variable we're using when we swap things. And then we've got a section where we can put what our items currently look like. So the first step would be to put all of our items in there. So these are the card numbers from earlier, you can see. So at each index, we have those cards. And then if we were to do one pass of a bubble sort, this is what your trace table would look like, right? So you can see after the items, we have our first pass. Our pass num is 1. We then, in the index column, we're going to count up from 0 all the way to 5, which would be the index of the second to last item. Look over here on the second to last column. And then temp is used when we're swapping a variable. So you can see I've highlighted in the table here when we're doing a swap. So at first, the 9 is in the first position. And then after we do the comparison, we've swapped them. Then you can see we get to the 10, and then we're going to carry that through and do our swaps. So this is an example of something you might have to do, right? They might give you a collection of items, and then you just have to do a trace table for a single pass. But yeah, like I said, we didn't have time to do it in the live stream today, but hopefully that gives you an idea of what this might look like. Cool. So now that we've seen a little bit about tracing, we've looked at some pseudocode, I've still got some more questions that I need to answer. So when we're looking at an algorithm to solve a sort of standard task, we might be asked to kind of comment on its efficiency. And some of the ways to sort of determine how efficient an algorithm is by looking at how many comparisons it's making. So how many times is it taking two variables and comparing them? How many loops is it doing? Is it doing unnecessary loops? Is it doing, too many? Is there a way we could stop it? And we also want to be careful of creating too many new variables that we don't do anything with. Now, in bubble sort, as we've just seen it, we have lots of comparing and we have lots of looping, but we don't really make that many new variables. We just have that temp variable, but we reuse that every time. So we don't really need to worry about the creating new variables for bubble sort. So we're just going to look at how many comparisons we're doing and how many loops we're doing. So the current version of bubble sort, the one I've just shown you, is not very efficient. There's lots of comparisons, right? We're going 2 by 2, we're doing comparisons, and we're doing that lots and lots of times every time we do a pass. And it just loops that inner for loop, just both the inner and the outer for loop, just loop until we reach n-1 or n-2 goes round. So we could probably do something to improve the efficiency there. So let's have a look at one way to make bubble sort slightly more efficient. Cool, so here's a new version of the algorithm. Now, much of this is kind of similar to what you've just seen, but let's talk about the ways in which it is different. So firstly, we have a swapped variable. So at the start, we're going to set swapped to true. And we're going to use this swapped variable to check as we're going through, as we're doing a pass, if we do a full pass and no items are swapped, that means that we already have a sorted list. So we can stop what we're doing and we can save some kind of computation time. We can stop doing our loops. So we're going to start by setting it to true. And then we're going to use a while loop this time. So instead of the outer for loop that we had before, which did that controlled the passes, we're now just going to do a while loop that will keep going while swapped is true. So while we're still making swaps, the while loop is going to keep going. At the start of a pass, we're going to set swap to false. So at the start, we haven't done any swaps yet. So we're just going to say swapped is false for now. Then as we go through, if we have to do a swap, right? If this if statement runs, we're going to set that swapped variable back to true, which will mean that our while loop will keep going. But if we get through an entire pass and no swaps are made, that swapped variable is still going to be false from when we set it up here, right? So our while loop will stop. So this is just one way we can save on some unnecessary looping. Now, we can also reduce the number of comparisons we're doing during this bubble sort. Now, at the beginning, I said that after each pass, one more item is sorted. Right, so after the first pass, the 10 was in the right position. After the second pass, the 9 was in the right position, right? And then we had the 8 and the 5. So what we can do is, by knowing that, what we can say is, actually, we don't need to compare the 9 or the 10 after they've already been sorted, right? We can cut out some comparisons. So we can just make one more edit to the bubble sort algorithm to make it slightly more efficient. Again, very similar to what you've seen. Let's have a look at the differences. I'm just going to highlight the differences in this new version. So now we are keeping track of the pass number, right? So we've got pass number equals 1 at the start. And then each time we complete a pass, we're going to add 1 to that pass number. So we're keeping track of how many passes we've done. And then we're going to use that to reduce the amount of comparisons we do in our inner for loop. So you'll see we're not going to num items -2 anymore. We're going to say -1 and then take away that pass number. So each time we do a pass, the number of comparisons will be reduced. Cool. So like I said, when we're looking at the efficiency of algorithms, we want to see how many comparisons we're doing, how many loops we're doing, and we want to check how many new variables we're doing. So hopefully that gave you a bit of an insight into how to test the efficiency and how to improve efficiency in an algorithm. So let's finish up with the questions that we did at the start. So number 1, why do we need to sort data? Because it's really frustrating to work with data that isn't sorted, particularly if that is really large. We just did 7 cards. Imagine if you had sort of 1,000 cards, it would be really, really difficult to work with them if they weren't sorted. Bubble sort is a standard sorting algorithm that uses a brute force technique to sort a collection, an array, or a list. It's called bubble sort because people like fizzy drinks, and they thought the way that the largest item moves to the end of the list resembled a sort of large bubble rising to the top of a glass. You can trace a bubble sort using a trace table and just following a pass through and keeping a track of that index and that temporary variable. And finally, when looking at an algorithm, you can assess its efficiency by checking how many comparisons it's doing, how many loops it's doing, and how many new variables it creates. So that is my whistle-stop tour of bubble sort. Oh, Pete, you're on mute. Pete, you're on mute.
Oops.
It looked amazing what you were saying, so I was just sad to be missing out on it.
I was just really excited. I was just saying that the Canadian computer cowboy lived up to his reputation, right, Laura?
Definitely, Pete, he did.
Thanks very much for that again, Mac. The way you use cards to show how the bubble sort algorithm operates really helped to explain each pass. Laura, I think we've got some questions for our audience, have we?
Yes, we have. And the first one is, Mac, can you explain why it is important to have that temp variable in the algorithm?
Absolutely. I'll just bring my slides back up because I think it's probably best to use the cards to show you this. Cool. So ignore the text on here for now. So when we are going through our list, actually, let's get one when we're doing a comparison. Sorry, I have to zoom through these. There you go. So when we're doing a comparison, so here I'm comparing the 10 and the 1. And because the 10 is larger, I want to swap them. Now, if I was just to say, set the last item in the list to be 10, that 1 would disappear, right? Because we'd overwrite it with the 10 that we've just assigned to that last item. So we don't want to lose that 1 because we want to swap them. So instead, what we do is we put the 1 in a temporary variable just to hold on to it for a minute. Then we set the last item to be 10. And then we can put the 1 back in the right position. And you can kind of see that on the algorithm here, right? So we take that item out, we then swap the 2, and then we put that temp variable back in. So just as a way of holding on to it for a little while so that we don't just erase it. Because once we overwrite a variable, the computer just goes, cool, I don't need to remember that anymore. It's off into the ether. So we want to keep hold of it.
That's great. Thank you, Mac.
That's really cool, Mac. I was just thinking, actually, with your cards there, you're almost showing that temporary variable when you had them above, like you put them in a different position. Do you know what I mean? So that was, again, that use of cards to illustrate it is really, really helpful. Thank you.
Yeah, absolutely.
You showed us how to make the bubble sort more efficient. Is there a more efficient sorting algorithm than the bubble sort?
Now, it's hard to say sort of categorically that any algorithm is more efficient. There are always situations. But in general, brute force algorithms tend to be slightly less efficient because we do things very procedurally. We go from start to finish. We do lots of loops, and inherently we do lots of comparisons. So instead, what we can use is a divide and conquer strategy. And there are sorting algorithms that use that. So the one we're going to look at next week, called merge sort, is a divide and conquer algorithm. And you will have seen this before. Anybody who's tuned into the previous live streams, if not, make sure you catch up on them. The binary search is an example of a divide and conquer strategy as well. So you can see how that one was more efficient than linear search. And so we're going to, show you a similar thing with merge sort, where it's a bit more efficient. But yeah, as I say, it's hard to say that any algorithm is definitively more efficient, but it's a different way of doing it that reduces loops and comparisons.
Cool, thank you very much. What are GCSE students expected to be able to do with the bubble sort algorithm you showed us today?
Cool. So GCSE students in an exam will be asked usually to do. They won't ever be asked to sort of code an entire bubble sort, start to finish. That would be mean. But they will be asked to maybe trace the algorithm, like you saw a minute ago with one of those trace tables. You might be given a copy of the algorithm with some lines missing and have to identify the correct line to put in. And you also might have to discuss the ways that a certain version of a bubble sort is inefficient. So you might have to comment on how many loops it's doing, whether it's using a swapped variable or not, and also whether it's reducing the number of comparisons each time. So you won't have to code the whole thing, but you just have to be able to discuss it.
Amazing. Thanks, Mac.
Oh, Mac, it's been great having you back. And we are certainly looking forward to learning about the merge sort algorithm on the 22nd of March.
Absolutely.
Amazing.
Yeah, that's awesome. Fantastic. Well, we can't wait. And we'll see you then, Mac. Thanks very much again.
Thank you. Bye, everyone.
As always, we put together some questions for you to test yourself on everything you have learned today. You'll find them in the chat and, of course, in the link below.
Let us know how you found today's session today. There you go. By filling out this form below as well. Below there. And if you haven't already, you can book a space for our session on the 22nd of March, by visiting our events page.
And we'll see you on the 22nd of March. Thanks, everybody.
On the 22nd of March. Bye-bye.